Oh, hello, everyone. Hello. Thank you for joining my sessions. I hope you are having a great day so far in Unreal Fest. It's finally last day, right? I'm Jisuban. I am a software engineer at Hyundai AutoEver. Today, I'm excited to introduce the world's first vehicle navigation system developed using Unreal Engine. I'd like to share our development journey as we work to render our maps in Unreal Engine. I will work through how we achieve this and highlight the key Unreal features that made it possible. And I want to take a moment to thank Epic Games for giving us this opportunity to present our project, and especially the Epic Games Korea team for all their support along the way. And I'd like to tell you a little bit about myself. I worked as a graphics engineer at Hyundai AutoEver, which is part of Hyundai Motors Group. And I've been working in the graphics engine development team for past 4 years. My team has been building our own in-house rendering engine for vehicle map visualization. And I've been focusing on integrating with Unreal Engine for real-time application. Before joining Hyundai, I worked on creating 3D CAD program at another company. And also I researched on physics-based simulation in the graphics laboratory at Korea University. I've been building my career as graphics engineer for about 8 years now. Before I dive into the details of our navigation system, I'd like to briefly introduce my company for those who might be unfamiliar with it. Hyundai AutoEver is the software specialist of Hyundai Motors Group. So we provide leading service and technologies in the field of mobility. We developed vehicle software for future vehicle, as well as digital transformation such as smart factories and digital twin platform, and core technology about cloud, big data, and security. Have you ever driven a Hyundai or Kia vehicle? Have you ever? Thank you, great, thank you. If you ever driven a Hyundai or Kia vehicle, you have probably experienced our in-car navigation systems. So Hyundai AutoEver is a pioneer in the in-vehicle infotainment system, driving the future of mobility. So we have accumulated advanced technologies and know-how in the GIS field. So we make sophisticated high-definition maps for navigation systems and autonomous driving. In the image you see on the screen shows our navigation system that was exhibited at CES this year. We collaborate with Hyundai Mobis and Mapbox to develop this navigation system, which features AI-driven 3D navigations and voice interaction. We are committing to helping you enjoy a new kind of lifestyle in your car, something you've never experienced before. And we are doing our best to make that a reality with many partners. So in-vehicle navigation systems has run on the embedded systems. So we have a restrict limits on the memories and CPU's uses. Even if we use the multi-core processor, the navigation system is typically limited to just one CPU core and have the available memory is usually less than 2 gigabytes. So even in these challenging conditions, we provide precise navigation by integrating HD maps and deep learning-based vision recognition for features like lane level guidance, indoor parking lot, and AR navigation. We are also developing realistic map using advanced graphics technology. Our high-definition maps and efficient software solutions are already being used in mass-produced vehicles. Plus, on top of everything I mentioned, all of our navigation features are available as a navigation SDK as well. So far, I will show you some of the latest technology in navigation systems. So now, the vehicle embedded systems and the autonomous driving softwares are evolving quickly, right? But that makes us wonder, what should the next generation of navigation look like? Well, we believe that the future navigation should offer users dynamic content and game-like visuals, and also interactive elements. So that's the kind of experience we want to deliver to our users. To figure that out, so we decide to try using Unreal Engine in our navigation system. So that's how our journey began. We are a team of 4 developers with strong native OpenGL ES backgrounds, but absolutely no experience with Unreal Engine. So we started this project by teaching ourselves Unreal from scratch. We started last year, so we begin from the how to spawn the actors and how to make a blueprint like this. So we carry out this project in 3 stages. First, we designed an architecture that could display the vector data in real time within Unreal Engine. We also checked the feasibility of applying various effects in Unreal. And next, we focused on the key navigation elements, such as building, road, and point of interest, POI, and checked if we could display them as well as the current navigation systems, and also whether we could apply better effects to enhance the content. For these 1 and 2 pages, we just focused on the visual quality and did not consider the performance. Finally, in the last pages, we integrate the essential module like search and route guidance. So the user experience would be our OEM navigation systems. We also optimize the performance and improve the rendering quality to ensure a smooth and high-quality user experience. So let me show you how we how we got all this done. The first thing we had to figure out when starting this project was how to process map data in Unreal. So unlike typical games, the data we use isn't packaged as assets. Our maps are based on the vector tiles. Pretty much all the major map providers, like Google, Mapbox, or OpenStreetMaps, use this format too. It all starts with a single label that covers the whole world. How far the cameras appears to be from the map determines the level of detail you see. So that we call the zoom level. As you zoom in, the entire world is divided into smaller chunks, and we call each of those chunks a tile. Each tile contains the map data in a vector data. It's not a mesh data. So as I mentioned earlier, instead of loading prepackaged assets, we download the vector data from online and load and parse processing and generate meshes in real time. We don't need to load all the tiles at once. So we only process the vector tiles that are currently inside the camera's view. To render vector tiles map in real time with Unreal, we design our system like this. First, the task of processing vector data is handled by the AutoEver map engine. We only handle the vector tiles that are inside the view system of the cameras in the map engine. Next, to render those in Unreal, we delivered the processed data to our UE plugin, which converts it into a U object meshes. Then the plugin creates the actors and components and place them in the Unreal world. You might be thinking, isn't it enough to just parse the data and process it and turn it into a mesh for rendering? But when it comes to displaying map data, there's actually another critical element to consider. It's the layer. Each tile does not just contain a single type of map data. Instead, it includes multiple features like background, vegetations, and waters, and roads, and buildings. So each of these features is described with geometry and metadata, so that we call layers. Just like you see on the screen, these layers of features are stacked up in order. So we actually drew the map using a paint algorithm. So we set up layer specifications that tell us the order to render each layer and how each one should look. So we need a structure that we deliver a layer specification. For each scene, we had to know which tiles are included, and for each tile, what kind of hierarchy structure its layers had. So we built systems to pass along this information, and we called it the AutoEver SceneGraph. Yes, it's the SceneGraph you know, but we redefine the node structure to fit the needs of the map visualization. We set up the SceneGraph so we can manage more than one scene at the same time. Because our map has multiple scenes showing at once. Each scene consists of several tiles, and each tile contains multiple layers, and each layer is made up of meshes. So for layers and the meshes netted with the tile, they are set up in a parent-child hierarchy, and each one uses a relative transform to their parent. Because the objects within each layers use normalized coordinates, which are defined relative to the tile they belong to. On the other hand, on the right side of the screen, you will see what we call instant node. These are not tied on the specific tile, and they created in real time based on the live data or triggered by certain events. So typical example of instance nodes are things like a POI shown up as an overlay and current location symbol that update in real time. Okay, so now we've covered all the elements need to display a map, and let's take a back and look at the big pictures, our rendering pipeline that combines both map engines and Unreal Engine. First, the map engine processes the vector data for each scene and converts it into a mesh primitive, which are then handed over to our UE plugin. And next, our UE plugin generates this into a U object meshes and caches them into a mesh pool. For each scene, the tiles and layer information is passed to by the SceneGraph. Each node in the SceneGraph is mapped 1 versus 1 to an actor in Unreal mode. For the lowest level mesh nodes, we attach the mesh components, but instead of creating new one every time, we fetch the pre-made U-mesh component and from a mesh pool. And by reusing these cached meshes, we reduce the CPU load, and everything can run much faster. When a request comes in, we instantly return existing mesh from the pool instead of generating them from scratch. This approach ensures the objects like roads and buildings and landmarks can be rendered in sequence, allowing us to efficiently build up the full map scene. So let's take a look at what type we used in Unreal Engine to render each of the map contents. First, for the map's base layer, the background, we use off-screen rendering to express each background tile as a single texture. For each tile, features like grass and waters and roads are drawn in order based on their layers G order. We use Unreal Engine's Scene Capture 2D to create this render target texture. The reason we draw background tiles as a texture is so we can apply a height map. By using both the backgrounds and the background textures and height map, we are able to represent terrain elevation. So Unreal Engine doesn't natively support the multi-words, so everything is rendered in just one word. To work around this, we logically split the map into 2 words in the base level. The 4 objects that need to be rendered off screen, we set up a word that physically separated from the main words. So what you see in blue is the main word where the background is displayed. And you can see an example of the tile meshes with the background material applied. And the texture parameters for the background materials is setting use target texture. A render target textures is generated in another word. In the separate word, we place and render the objects that make up the background. Then using the Scene Capture 2D components, we capture the scene's view and create the 2D texture. Next, let's talk about how render the buildings. Buildings are one of the most important features for helping users understand their own locations and surrounding environments on the map. So there are actually 2 types of buildings on the map. So first, we have regular buildings, which are to create the various building polygon based on their footprint and height information. In Unreal, we use a procedural mesh for it. And second type is a landmark. We didn't use the pre-built static mesh assets for landmarks. Instead, we load the GLB files in real time and dynamically create a static mesh component using the GLTF runtime, which is the third-party plugin. And nature elements like trees and waters on the map is a crucial role in helping users understand their surrounding. The last lake or the park in particular acts a key landmark that makes it easier to maintain their sense of direction. For tiles, for trees, we place the instance static meshes based on the real-world coordinates of actual street trees. As for water, we create a dynamic water surface by animating a normal map to simulate realistic waves and ripples. This effect was applied in the background materials post-processing stage using both normal and specular properties. By combining realistic trees and the dynamic water animations, we are able to build a map that feels much closer to the real driving environment and helping drivers feel more connected to road. And the route line is implemented using spline component. As soon as you start your drive, the route line is created instantly as an object that isn't tied to any specific tile. For precision load elements like lane level, lanes and load marks and crosswalk, we use procedural mesh for it. While displaying these details with great accuracy, we can also provide true lane level guidance, including feature called carpet view that shows you exact which lane to follow. Lane level guidance help reduce the unnecessary lane changes and improve traffic flow and creating a smoother driving experience. POIs are on the key elements of the map. We can display them as an overlay using UMG, user motion graphics. And one of the great things about this is that we can easily edit widget properties right in the editor, like change the symbols or adjusting the text and the symbol alignment, and see the result instantly without having to rebuild. This was a huge advantage for us because it meant designers and developers could work together and immediately see the impact of their changes. So we make the whole development process much more efficient and faster. After displaying all the essential map contents, we set up multiple scenes. On the right side of the screen, unlike the main maps, which focus on the ride guidance, this additional scenes was designed to give much more detailed view of surrounding vehicles and environment. So we set up a separate world physically placed away from the main world, and it's just for the details view. Since the main map and each additional maps are loaded and composed independently, so we can display different contents and styles in each scene. That means the main maps and the detail view can each have their own unique look and informations, and they can be shown at the same time without interfering with each other. And finally, we experienced with the various lighting effects on the map. We adjust the sun's position to reflect real world. Changes in lighting depends on the time of day. It allows to control shadows and brightness and color themes, and to create smooth transition from day to night, which really boosts a sense of realism. For the landmark, we use light map to achieve the building illumination effects. By doing this, we can make our landmark stand out and make the map more beautiful. When we first packaged the complete map, ran it on an Android device, we faced the major challenges. Whenever we moved the map and new areas be loaded, we experienced severe frame drops. So to figure out what was causing this, so we used the Onion Insights for profiling. So we cover the where frequently spawn and response the new actor for our SceneGraph. because we are constantly loading the new vector tiles and generating meshes in real time. To solve this, we focus on the optimizing how actors are spawned and registered. After making this improvement, we are able to reduce the frame time by about 50% on Android device. So how did we actually optimize this? The answer was object pooling. In typical PC game, where the resources are plentiful, so you might not need to worry about this kind of things. But in our case, we run on the embedded system, so we need to consider it. So because spawning actors can only be done on the game thread, so we could not just upload it to another thread for the better performance. So to get around this, we create a pool of actors and components ahead of time. Whenever we need to build a scene, we just reuse the one we've already made and just reset them after each use, instead of always creating and destroy them. By increasing the reuse rate of the actors, we are able to significantly reduce the load on the game thread. As a result, we doubled the frame rate and everything's run much more smoothly. So, okay, that's what we do. There's the result from our phase 1. In phase 1, we built the basic structures and tried out a variety of different features that Unreal Engine makes possible, like displaying a wide range of buildings and implementing time of day and light events. For the phase 2, we focused on making the map feels even more realistic. So we added things like landmarks and day and night modes, and details like trees and water surface. All of this made the map much closer to what you'd expect from an actual navigation system. In phase 3, we focus on improving the performance to achieve the faster response times. And we also applied the anti-aliasing for cleaners and higher quality visuals. And we added essential navigation features like search and route guidance. All of these enhancements help us drivers can smoother and more seamless navigation experience. We didn't just stop to displaying the map. We also explored the possibility of building AR navigations using Unreal, and confirmed that it's definitely possible. Looking ahead, our goal is to integrate the navigation modules with a different level, and so everything can run together as a standalone applications. This will let us offer a variety of view modes and create an even richer navigation experience for our users. We've also experimented with exciting possibility with PCG. For example, we could build entire buildings by combining building modules like windows and walls. So we didn't have to create a building polygons manually. And also, we confirmed that we can place the trees and other vegetations like grass in a natural way in selected areas. So even if there's no raw data for those areas. Moving forward, we plan to apply more of these features to create even more realistic and game-like visual fidelity in our maps. So there are a lot of things we really liked about using Unreal Engine for this project. First, it made us way more productive. Working together with designer in a single tool meant we could instantly share the results without having to rebuild the project every time. So this made collaboration much smoother and really sped things up. And also, Unreal's built-in rendering and lights solutions made it easy to achieve a high-level visual fidelity, letting us apply effects and represent objects right out of the box. So no need for extra builders or complicated shader setup. So this really lowered the technical barriers. And on other things, Unreal offers a great extensibility. So thanks to its well-established marketplace for plugins and assets, it was super easy to expand our project whenever we need to add new features and content. So for these reasons, we really believe that our project has unlimited potential with Unreal Engine. So going forward, we are planning to take things even further. So this video is our target made using Unreal. And this is the concept. For example, we are bringing in real-time traffic lights data and visualizing it right on the map. Actually, real-time traffic lights are already available in some areas in South Korea. And we also want to use the more of Unreal's feature like PCG to make our maps even more realistic and detailed. Plus, by using vision recognition, we are able to add dynamic contents like animations for nearby vehicles and pedestrians. So the maps feel much more alive. So our ultimate goal is to give drivers the most accurate information possible and to develop the navigation system that fit for both autonomous and next-generation vehicle. If your company share our visions and you are interested in trying out our product or just want to know more, please reach out us at the emails below. We always open to new partners and collaborations and new ideas about what we can build together. And that's all for today. And before I finish up, I'd like to give a special thanks to Suyeon, Gite, and Useo, who worked with me this project, and as well as the entire graphics engine development team. Yeah. Thank you.